Next, we're going to be taking a look at limits of even root functions. So that means that the index of the radical is an even number. All right, so the first thing we're going to do is plug in the x value into the function, just like we did with logarithmic, trigonometric, polynomial, etc. functions. Then we're going to figure out what we get back. Now, here's the thing. We're going to go ahead and pull up a graph of an even root function. Notice what happens, for example, at 0, 0 of this graph. The limit from the right is equal to 0, but the limit from the left doesn't exist. At that endpoint, there is no limit, okay? The limit has to be the same from the left and right. If it's undefined on the left, it won't exist. We can do this for different radical functions. Let's say it's, you can see the function there, negative square root of negative 5x plus 5 plus 3. Again, at this endpoint right here, the limit as x approaches 1 from the left is equal to 3, looks like. But the limit from the right doesn't exist because there's no graph on the right. And so we are concerned about what's going on inside the radical. What's inside the radical can't be equal to 0 because when it does, that's when we have this endpoint right here. And so what we want to do when we're looking at the rules for this is if you end up with 0 inside of the radical, then that limit will not exist because it's going to be basically a dead end. Now, if it does exist, just like the other functions, just like this page we looked at, if it does exist, then it's going to be equal to the function value. If we go back to this graph, let's say we find the limit as x approaches 0, you can plug in 0 and you get negative square root of 5 plus 3, whatever that is, okay? Maybe we want to plug in negative 4. It makes a little bit more sense. If you plug in negative 4, you get negative 2 back. That's going to be your limit. So everywhere else but the endpoint, the limit's going to be equal to the function value. The endpoint is what matters. And again, if you get square root of 0 back, that's going to tell you that the limit's not going to exist for that particular radical. So let's take a look at an example of what that would look like. Let's say you have the limit as x approaches negative 3. Didn't mean to do that. Limit as x approaches negative 3 of 2 plus the square root of x plus 3. So let's go ahead and plug that negative 3 into the function. But look, we get square root of 0 right here. And so we know that's going to be an endpoint, just like it was an endpoint right here on this function. Because if you were to plug in 1 here, okay, you would get 0 in the radical, and you can see at 1 that's an endpoint. All right, it's an endpoint because anywhere to the right of that's going to be undefined. And it's the same as if we have it coming from the left. Let's see if we can randomize it. And yeah, so if it's coming from the left, say for this one, if we plug in 6, we're good from the left, but from the right, we're not. Why? Because if we plug in 6, we get 0 inside the radical. So that's important. Whenever you get 0, that means the number you plugged in, the limit doesn't exist there. So therefore, for this graph, limit as x approaches negative 3 of 2 plus the square root of x plus 3 does not exist because we got 0 inside the radical. I do want to take a look at another even function. Let's say we plug in 2 into this particular function. When we plug in 2 here, we get negative 1, okay? Why is that? Because it doesn't exist. We get square root of negative 1, which doesn't exist. Why is that? Because a radical function only exists on one part of the graph. Like, for example, right here, if we would plug in 8, we'd also get a negative number inside of this radical. We get square root of negative 2. And so square root functions don't exist everywhere. And so the point of this example is if you plug a number in and it doesn't exist, then the limit's not going to exist for that radical function because it's off the graph completely. There's nowhere to trace it. So keep that in mind when you're plugging in numbers and it doesn't exist when you plug it in, then that means the limit doesn't exist. Now for this even root function, when you do plug in, let's say plug in limit as x approaches 3 of square root of 4 minus x. When you plug in 3, you actually do get the square root of 1 back, and that exists. That's 1. Okay, so since you do get a number back, the limit is going to be equal to the function value, and therefore you can just say the limit as x approaches 3 of 4 square root of 4 minus x is equal to 1. Again, it goes back to the fact that as long as it's not that endpoint, the limit is going to be equal to the function value. I will say one more thing before I finish this lesson. This is true for a lot of other types of functions. If you're plugging a number into a function and it doesn't exist, All right, so this might be for logarithmic, trigonometric, or any other function, and you're not sure whether or not it does exist. Like let's say you get 1 over 0 or something, and you want to be sure, especially for logarithmic and trigonometric functions, but any function this will work. Just use the chart method that we talked about. So if f of c does not exist, then what you want to do is you want to make charts, and you want to approximate to see what those values are approaching. Like we said before, sometimes we have to resort to the charts because there aren't special rules to figure out those particular limits. And so as we progress and learn more rules, you'll figure out that sometimes we can't use rules and we have to resort to the charts. So that's limits of even root functions in a nutshell. I didn't talk about this before, but in an odd root function, the limit's going to be equal to the function value because the domain is all real numbers. So if you have any other questions about limits of radical functions, let me know.